All right, it's my pleasure to introduce our first speaker of today, Allison Wise. She is currently working on her master's degree at Auburn University under the guidance of Dr. Tim Bruce. She did her undergraduate at Texas Lutheran University with a bachelor's in molecular biology with minors in chemistry and French. And outside of the lab, she likes painting and fishing. So take it away, Allison.
All right, so like you mentioned, I'm Allison Wise, and my project now at Auburn is looking at co-infective bacterial pathogens in channel catfish. So just as a quick overview, I'm going to go over the major bacterial pathogens that are in the catfish industry, then go over some bacterial co-infections that are seen in the industry, then go into how I'm going to assess these co-infections with my trial design for trials 1 and 2, looking at bacterial co-infections between Edwardsella ictaluri and Flavobacterium coviae for my first trial. And then for the second, I'll go into looking at virulent Ehrmonis versus F. coviae in channel catfish. So the U.S. catfish industry is the largest aquaculture industry in the United States. And the Southern economy relies heavily on the industry's revenue, bringing in about $398 million in 2021. And outbreaks of disease drastically impact production. So producers have to manage outbreaks associated with different pathogen types. Usually bacterial, parasitic, and viral pathogens can affect the catfish industry. So like I mentioned before, the outbreaks do drastically impact mortality and will affect the industry's economy. So bacterial diseases account for about 60% of channel catfish losses. And this is mainly attributed to 3 major bacterial pathogens in the industry: Edwardsella ictaluri, Flavobacterium columnare, which has now been renamed to F. coviae, Flavobacterium coviae, and virulent Ehrmonis hydrophila. And losses associated with single infections for each one of these pathogens is about 60 million for E. ictaluri, 30 million for F. coviae, and about $35 million in losses for virulent Ehrmonis hydrophila. And recently, about 78% of production operations have experienced E. ictaluri and F. coviae outbreaks concurrently. So that does indicate that co-infections do exist in the industry and can cause severe economic losses. And just as some clinical signs associated with these 3 pathogens, E. ictaluri is known for the cranial ulceration, and which is now typically known as hole in the head. It can also have hemorrhaging and exophthalmia. F. coviae is known for causing a saddleback lesion on the dorsal fin of the fish, also with skin and gill necrosis. And virulent Ehrmonis is known for having hemorrhaging, exophthalmia, and internal and external hemorrhaging as well. And this slide here is just some images showing these clinical signs. So in the top left is a fish that was infected with F. coviae, and you can see the bacterium growing on the gills, which will restrict oxygen to the channel catfish. And then to the right is a photo of a fish infected with E. ictaluri, which is, you can see the hole in the head. And then underneath is a fish infected with virulent Ehrmonis. You can see some ocular hemorrhaging, exophthalmia, and internal and external hemorrhaging. So first off, what are co-infections? Co-infections occur when 2 or more pathogens infect a single host at the same time, and they can occur with multiple different pathogen types. So you can have bacterial versus bacterial co-infections, or you can have bacterial and parasitic co-infections. So really any combination of pathogen, as long as there's 2 or more, is a co-infection. And then bacterial co-infections often go underreported in the catfish industry, which this leaves us with the lack of knowledge of the true prevalence of co-infections. And it also will leave us with a lack of understanding of how co-infections interact in the host. So pathogens can compete for host resources, and this can lead to either synergistic or antagonistic infections. So a synergistic infection would be when 2 pathogens work together to obtain host resources, while antagonistic infections would be when one pathogen will suppress the other in order to obtain the host resources during infection. So just as a quick history of co-infections in aquaculture, co-infections are abundant across multiple aquaculture species. They've been seen in zebrafish and have been evaluated looking at Ehrmonis hydrophila versus Ehrmonis veronii infections. They've been seen in rainbow trout, looking at IHNV with Flavobacterium psychrophyllum. And they've also been seen in channel catfish with a parasitic versus bacterial co-infection, looking at a trematode bulbophorus versus E. ictaluri. So there has been a prevalence of diagnostic cases that have been demonstrating and pointing towards multiple pathogen infections in the industry. And what we really want to know about these infections is it primary, which pathogen is primary and which is secondary, so which is actually causing disease, and then which is just adding on as an opportunistic pathogen. And understanding this dynamic can lead to optimized treatments, because currently treatments are limited to very few antibiotics. And we really want to make sure and ensure that we're treating the correct pathogen with the correct antibiotics. And this can be difficult with co-infections because they're obviously multiple pathogens. So in order to assess these co-infections, I designed 2 trials, like I mentioned before. Trial 1 was Edwardiella ictaluri versus Flavobacterium coviae, and trial 2 looked at F. coviae versus virulent Aeromonas hydrophila. And in each trial, I investigated the same parameters listed here. So I looked at cumulative % mortality, so I can make comparisons between mortality in the co-infected groups versus single infected groups. Also looked at an array of immunological assays, looking at serolysozyme present in the different co-infection groups, and then bacterial load along with gene expression, looking at 3 different pro-inflammatory cytokines and 1 immunosuppressant gene. So for my first trial, I have 5 treatment groups. I looked at a full dose with a single infection of E. ictaluri, and then a full dose with a single infection of F. coviae. Now, for my co-infection doses, how I did it is that I would give the pathogen, so whichever one, in this case, ictaluri first, and then wait 48 hours post that immersion and give it the second pathogen. So for the third group, it's a co-infection with a half dose of ictaluri, and then 48 hours later, I gave it a half dose of F. coviae. And then for my other half dose co-infection, I reversed that. So I gave it F. coviae first, and then 48 hours post exposed it to E. ictaluri. And then of course I had my mock controls. And my mock controls, since both bacteria are on different media types, were given sterile PBS. So just for my challenge conditions, the challenge was conducted between 27 and 28 degrees Celsius at a 0.5 liters per minute flow rate. And then for my doses, I gave the ictaluri full groups 6 mils into 10 liters and bathed it for 30 minutes with no flow. And then I did the same thing for F. coviae, but instead did it with 110 mils into 10 liters, immersed it for 30 minutes as well. And ictaluri, the full groups got delivered a 0.5 times 10 to the 6 CFU per mil. And for F. coviae, the full dose got 3.6 times 10 to the 6 CFU per mil. So these are just some diseased fish from trial 1. As you can see, the ictaluri fish has some hemorrhaging, some ocular hemorrhaging along inside of it as well. It had a lot of internal hemorrhaging. And then for the single infection F. coviae, you can also see the saddleback lesion that is typical of this type of infection. And then when you go into the co-ictaluri groups, you can see a mixture of both clinical signs, a lot of hemorrhaging of the head, along with the saddleback lesion, and it also had a lot of internal hemorrhaging as well. And then, however, for the co-F. coviae group, there really wasn't any external hemorrhaging at all. It was mostly dominated by saddleback lesions and fraying of the fins. And internally, however, there was again a lot of internal hemorrhaging. Now, for my CPM data, unfortunately, FC didn't cause significant mortality in the single dose, and my E. ictaluri single dose experienced about 90% cumulative mortality, making it difficult to make comparisons. And though mortality was primarily driven by E. ictaluri, deceased fish from the co-groups presented clinical signs associated with F. coviae, and F. coviae was re-isolated and present on plates that were cultured from fish that had died in those tanks. So the co-groups experienced an ictaluri infection with a subclinical F. coviae infection. And even though it is fairly difficult to make the comparisons between the co-groups and the single infection groups, It is interesting that there was a delay in mortality between the co-H. pylori and the co-FC groups, as you can see with the orange and blue lines in the graph. For co-H. pylori, mortality began about 4 days post-inoculation, while for co-F. coviae, we didn't see exponential mortality until days 8 or 9. And initially, I thought this could be due to the fact that the co-FC group got H. pylori, the H. pylori pathogen, 48 hours after, and this could account for this delay. But even taking that into account, there's still a 3-day delay between the two groups. So this could be attributed to a biological relationship with the subclinical FC infection. But this relationship needs to be further evaluated in order to make that conclusion. So this is really what we have for here. And then future trial work is going to be done in an attempt to increase the mortality for the single infection FC group and decrease the mortality for the single infection H. pylori group, so we can make better comparisons between co-infections and single infections. So for my lysozyme data, as you can see, every group followed the same relative trend, where at 4 and 7 days, it had its peak amount of lysozyme, and it was significantly different between 2 days post-challenge and 21 days post-challenge. And similarly to the mortality CPM data, the groups that showed the most lysozyme were the E. pylori and both co-groups. And this is primarily due to the H. pylori being present as well. And then for my gene expression data, similar results were found that in the H. pylori, co-H. pylori, and the co-FC groups, we saw the most expression of the IL-1 beta gene. And we saw that it was highest at 7 days, and it was significantly upregulated compared to 2 to 4 days post-inoculation. And once we go, similar results were also found in the other pro-inflammatory cytokines that we investigated. So for IL-8, once again, we had the highest expression seen at 7 days, and it was most abundant in the H. pylori and both co-groups. And once again, same was seen for TNF alpha gene expression. So at 7 days, it had the highest amount of gene expression, along with the same groups, H. pylori, co-H. pylori, and co-FC, that had the highest amount of that gene in those groups. However, when we look at TGF beta gene expression, you can see that it really did not change throughout the course of infection. So TGF beta is a gene that's responsible for suppressing the immune response. And this lack of expression shows that the pathogen doesn't really elicit an immunosuppressive response from the host, so that these infections primarily drive a pro-inflammatory cytokine upregulation during the infection. So for trial 2, I changed a lot up with the trial design. So there's more groups in this trial because I really wanted to look at how the doses really affect it. So I wanted to look at full doses and half doses in both the single and co-infection groups. So I gave a full dose of single infection of Aeromonas hydrophila along with a half dose of single infection Aeromonas hydrophila, and then a full dose single infection of F. coviae with a half dose single infection F. coviae. And I also changed up how we delivered the pathogen to the co-infection groups. So as y'all probably know, in order to induce infection with virulent Aeromonas hydrophila in trial work, you have to clip the adipose fin. So I wanted to make sure that both pathogens were exposed to the same conditions. So I clipped the adipose fins of all the fish. So every treatment group had, all the fish were had their adipose fins clipped. But this also prevented me from doing the 48 hours post second dose. So this time I gave both pathogens at the same time, and all fish were fin clipped. And so I did that in a full dose with the co-infections of both pathogens and at a half dose. And then again, for the mock controls, they received sterile PBS. So this is some diseased fish from trial 2. You can see in the full F. coviae group, like we saw before, that you have this saddleback lesion and a lot of frayed fins. And then for the full VAH group, we see this ocular hemorrhaging along with hemorrhaging in the fins. And they also both had a lot of internal hemorrhaging, just like we saw in the first trial for F-CoV. And then for the full co-infected fish, we saw some hemorrhaging externally around the gills and on the head. And we really saw a lot of fin fraying and degradation of the skin, as you can see in these diseased fish, a lot along with some exophthalmia. And it also experienced a lot of internal hemorrhaging as well. So just like in trial 2, co-infected fish demonstrated clinical signs associated with both pathogens. And so for our CPM data for trial 2, turned out a lot better. As you can see, the co-infected groups greatly increased mortality. Even at a half dose, the co-infected groups greatly had a lot more mortality compared to the full dose of each single pathogen. So here we can make conclusions and say that F-CoV co-infections can increase mortality substantially compared to single infections with F-CoV and virulent Aeromonas hydrophila. So my next steps in this trial, so like I mentioned before, I will redesign trial 1, and this will also allow me the opportunity to include these half doses, as well as I'm gonna try to increase the dose for the FC fish to have a higher mortality and then decrease for the E. pylori treatment groups. And just as a summary of what this trial gave us, the immune responses for single and co-infected pathogens have been discerned. We were able to look at the innate side of the host immune responses, looking at pro-inflammatory cytokines and an immunosuppressant. And we were able to say that, E. pylori infections don't really cause an upregulation of immunosuppressants in channel catfish of that gene. And we also saw an apparent change to infection of the dynamics in trial 1. But once again, this redesign of trial 1 will allow us to better make comparisons between the two groups once we get the doses down. And we also saw that co-infections can increase mortality in trial 2, which is the graph I just showed y'all with F-CoV and virulent Aeromonas hydrophila. Also, more work can also be done evaluating other co-infective pathogens in channel catfish. So you can look at how some pathogens can create a portal of entry, allowing opportunistic pathogens to infect the host as well, along as looking at how F-CoV can create a portal of entry with the saddleback lesion for the Aeromonas hydrophila instead of doing a fin clip. So those are just some different avenues and more trial work that can be done in the future to look at co-infections. So understanding host immune responses is really important in order to find targeted treatments that will be successful in co-infections. And identifying clinical signs also will help sooner detection, which will also help the treatment as well. And understanding a true prevalence within the industry will also allow us to really see the effect co-infections have in an industry setting, which will once again help us ultimately get better treatments. And I'd like to thank everybody, my project team who helped me with this project, including Dr. LaFrance, Dr. Kelly, Dr. Lyles, Dr. Beck, Dr. Griffin, and Dr. Bruce. I'd also like to thank my lab members who helped me with this project, including Guillaume Kako, Courtney Harrison, and James Tuttle. And that is all I have for y'all.
All right. Thank you very much, Allison. Virtual round of applause for you. Very nice presentation. Folks, if you have questions, feel free to drop them in the chat, or you can unmute yourself. And Bart, we'll start with you.
Hi, Allison. Congratulations for a very nice talk. I would like to point out, focus your attention about the early stage of the immune response against those pathogens, because you checked only one marker for immunosuppression, which is TGF-beta. But actually, I would like to suggest you to focus more on other markers like IL-10 and SOX genes.
Okay.
Because they may provide you better indication about a potential immunosuppression going on at the early stage, rather than focusing on day 7, because actually you're showing some very interesting data, because in the co-infection group only, there is a higher induction of the pro-inflammatory genes. when comparing to each single infection. So I think it's a matter of marker selection, but you may get very interesting results there. And also the delayed mortality.
Yep.
It is something very interesting. It was just a comment, but
Yeah, no, thank you. I appreciate it.
You're welcome.
All right, any other questions out there?
Hey, Allie, I'll go. Great talk, as always. Really enjoyed that. Just out of curiosity, right? We see columnaris all the time, right? You see columnaris with trematode, you see columnaris with hamburger gill, you see columnaris with ictaluri, you see columnaris with aeromonas, you see columnaris with, Pysocida, etc. So, the general kind of dogma is a lot that columnaris seems to be more secondary than primary. Based on your results and kind of what you've seen, what do you think about that?
I would still think that in this case, that F. coviae was more of a secondary infection. Even when we looked at, when compared to ictaluri, but even when we looked at the trial 2 F. coviae, so with it in virulent aeromonas, which was really interesting because both of those in research have been seen to be more opportunistic pathogens. They kind of just really blew it out the water when they were together. So it's hard for me to say that, like, in trial 2's casework or trial work, that one was, primarily the pathogen over the other. But definitely for trial 1, I would say ictaluri was definitely the primary, and F. coviae was more of a secondary. But I also can't say that definitively because we weren't able to get the dosing where we needed them to be to make those comparisons. So that's really what I'll be looking at in this trial work that I have going on now with the redesign of trial 1. But I would still say for sure for the first trial that F. coviae was probably more opportunistic. And then in trial 2, that's a super interesting point because both of those are mostly opportunistic, and they also have really the same timeline when it comes to mortality. So like for F. coviae, we saw mortality hit both times around like 48 hours after. And then for Aeromonas hydrophila, you really see mortality start hitting at like 12 hours to 48 hours. So they both kind of hit the fish at the same time when it comes to the time of death. So it's really interesting.
So yeah, I mean, so out of curiosity, here's a chance to kind of expand on that. What would you do differently to, if you wanted to better parse out, what is more likely to be a primary versus a secondary or opportunistic infection?
Initially, I thought it'd be a good, I don't know exactly how that would end up working, but I thought giving them, presenting them with the pathogens at different time points, like with that 48-hour delay, like we did in trial 1, would let us see a little bit more into what's actually going on the front of primary or secondary, but it did not work out there. And yeah, I definitely need to do more work in that front to try to tease that out.
Yeah, certainly. Those interactions are extremely complex, and so I mean, it's not an easy question to answer. But yeah, good stuff, Allie.
Thank you.
All right. Any last questions before we move on? Okay, well, thank you very much, Allison. Great presentation, and good luck with the future of it.
Thank you.